distinguished seminar series, which is sponsored by the Department of Civil Environmental Engineering, the Chang-Mei Fund. So I'm Professor Guriba in the department. And this term, we're going to have a series of exciting speakers, starting today with Professor Zhang, and I leave the introduction to Professor Osorio to do. And I just want to do a little bit of advertisement for the next few talks that are coming. We're going to have Professor Chris Field, who's going to also talk about climate. Harry Sweeney, who's going to talk about universality, nonlinear dynamics, and fluid dynamics. And Simon Levin, or Levin, depending on how you pronounce, that is going to talk about various topics touching from ecology, multi-scale modeling, and possibly also maybe nonlinear dynamics. So welcome to this series, and I hope that I'll see you coming back, and I'll leave the floor to Professor Osorio.
So it's my pleasure to introduce Professor Michael Zhang, visiting from University of California, Davis. He's an expert in traffic flow theory, traffic operations, dynamic traffic assignment, network optimization, intelligent transportation systems, and he's done a lot of work in what we call macroscopic traffic flow theory, which he'll talk about today. He is also a member of the TRB, the Transportation Research Board Traffic Flow Theory and Characteristics Committee, and is an area editor in Transportation Research Part B. And I just learned a few minutes ago that he'll also now be an area editor in transportation science, and he's extensively published in all the top transportation journals. So it's our pleasure to have you here, and we look forward to this talk.
Thank you, Carolina. And I want to thank my two fantastic hosts, Lydia and Carolina, for the invitation and hospitality. And it's a great pleasure for me to give the first talk of the year. So today I would like to share with you my understanding of traffic flow and how that applies to the everyday life traffic problems. So, I'll give a very quick overview of the problem that we face about traffic congestion, and then how that relates to the driving behavior, and how we can, from the driving behavior, we derive some of the traffic models, and then use this model to explain the everyday congestion phenomena, some of the puzzles that you may wonder, and then how we can apply that to manage traffic congestion. And then finally, I'll give an outlook of the field. So one of the reasons we study traffic flow is because the traffic congestion, whether it's on the highways or at seaports or airports or bus stations, it permeates our everyday life. And it, according to a report, Urban Mobility, it cost a tremendous amount of waste of fuel and delay and also dollars. You can explain traffic congestion by simply saying that the supply is not meeting the demand. In the case of highways, we can see the vehicle miles traveled over the years in the United States, and we can see the lane miles built in the United States, and this gap has become bigger and bigger. And can we just build more roads to eliminate congestion? Well, we could, but the thing is that congestion is, in human activity, is very unique in the sense we have very unique peaks. This is a morning peak on a highway and this evening peak, and it would not be economical to build the way at the peak because most of the time you're not using that capacity. So congestion will be with us in some form. So we'll have congestion just for economic reasons. And for that reason, we have to study congestion. And also we wonder, there are flows in nature, and whether it's materials or whether it's animals, can we learn something from those fields? And the answer is yes or no. And no. Yes is, if you look at a congestion road, and it resembles a lot like a river flow, right? So maybe we can use the models in river flow to apply to traffic. Actually, the classical model that we use to study traffic was developed by a fluid mechanician, Lightwell, and probably people know, and then applied mathematician and G.B. Witham. So the light algorithm Richard's model, and they actually modeled the river flow, and then they have two papers. One is model river flow, and the other is highways. But there are differences also significant, because in the river flow we have natural laws to apply, the physical laws in conservation of mass and momentum and energy. But in the highway, of course, we have conservation of mass. The vehicles don't disappear, right? But then we don't have equivalence of momentum energy to guide it. So I would call a conservation of life. We want to be safe. We don't want to, get into accidents. But those things are concerned about safety, speed, and comfort. So they are behavioral laws. They are not physical laws. Okay. So as a result, we know that when a river narrows, the water flows faster. But we never see when road narrows, the traffic moves faster, because the mechanism is quite different. So we have to look at the behavior of drivers and how that affects the flows. I think, So also in nature, there are other flows that we observe, like the flocking of birds and fish and the movement of ants. And these systems, using very simple rules, but you can develop very complicated patterns, and we never saw congestion on ants traffic. So the human intelligence, we think we are, more intelligent than those, and we can build airplanes and build cars, but in organizing traffic, we have a lot to learn from these simple systems. And you have, in optimization, you have ant algorithms, so people start to develop so-called swarm intelligence and to mimic the rules that used in these systems to organize the traffic better. So there is something to be said about that, and we have to learn from them to organize our traffic more smoothly than, like in this case, everyone gets stuck in this intersection that perpetuates on the other roads. So what's this? So what's unique about driving and actually driver behavior and the human traffic, the vehicular traffic? Actually, driving is a very complicated task. The steering and the acceleration, deceleration, and many of us spend hours after to learn how to drive. Although now, after a while, you probably don't realize how complicated it is. It's a very complex feedback system, control system. We have to sense the distance, the angle, the turning, and all these things. So here, in terms of traffic flow, there are two things that are very critical. One is the speed spacing control. So for a given speed, how much space you're going to leave, or for a certain space, how fast you should drive. And also the lane keeping, not just the steering, but which lane you want to travel and when you want to switch lanes and so forth. So I was wondering, when you drive, what rules do you apply? Probably, it's been a long time ago, you probably don't even think about it, right? But when you first learn how to drive, people give you recommendations. What kind of recommendation people give you? For the, let's say for the spacing, for the spacing, speed, and for a given speed, how much space you should keep, or for a given spacing, how much speed what speed you should drive. Have you remember some of these rules? Yeah.
For every 10 miles an hour, you want one car length.
Great. That's one of the rules. Yeah. Do you apply that in real driving? You probably are consciously.
I don't drive it.
Oh, okay. So much about rules. And are there other recommendations? So that's one I call one car length rule. So for every 10 miles per hour speed, you keep one car length. And there's also other recommendations. I call it 1001 rule, is that when you're driving, you count 1001, 1002, 1003, and you should travel the distance between, the gap. So in either case, if you look at this, the car length divided by the 10 miles per hour, so that gives you a unit of time. So, okay, so you have some kind of a time. In this case, it directly recommends you to keep that time, and the 1001, 1002, 1003, and you count it and see how it does. So let's look at these rules and translate that into a mathematical model. Okay, so let's say this is a front car with a travel speed u, and this is a car behind with a travel speed v, and this is the spacing that you should keep, that we call the space gap, and this is the spacing that including the vehicle length. Okay, and we need this because we convert that into density, then we have to consider the vehicle length on a mile, and this is the position and of the two vehicles. I use the end, you can use the front bumper as well, then the vehicle length will be the front vehicle. So let's start from these two rules and see what we can get. So I already described that, and then, so mathematically, if you look at the first rule, it's the space you're living, it's speed divided by the 10 and times the vehicle length, right? So that translates into that rule. And then if I use L divided by T to be a capital T, and this is some time constant. So the space gap equals velocity times the time constant. In the second rule, basically my distance traveled at this speed have to be given by the time constant. I counting 1,000, 1,000, 2,000, 3. Although I use the same symbol, but these two constants can be different. You know, you can vary, but for convenience, I just use the same symbol. And both of them, you rearrange terms, you can get this equation. It's the velocity you're driving depends on the time gap divided by a time constant. And that, when the time gap is very large, then you can get a very high speed, which is not realistic, right? So we have to constrain that by the speed limit. So adding the speed limit, then you get this relation. It's basically the velocity you're driving, it's the minimum of, if you're driving at the maximum speed, then you keep on that maximum speed. But if you're not, then it's determined by this term. So that's the based on that rule, what we get from the model. And then I translate into a differential equation, which is, this is by definition, the position derivative equals velocity, and this is derivative of velocity equals acceleration. And you look at here, the acceleration is either 0, if you get maximum speed, if you cruise, or it depends on the speed difference between you and the front vehicle. And if you're driving slower and this is positive than the front vehicle, then you accelerate. And is positive. If this is higher than the front vehicle, and then you decelerate. That makes sense, right? So you get that, and then I rewrite this term into, because this is really this derivative of spacing. So I can have dv dt equals ds dt. And then at steady state, so every vehicle travel at the same speed from one velocity transition to another. And if I integrate the equation, I get a steady state relation of v, a function, velocity function spacing equals minimum vf, and then this relation. And if you draw the curve, it looks like this. So your speed is linearly increasing with spacing, and then once you reach maximum, then you cap there. And if I use 1 over spacing as the density, which is the vehicle number of vehicles per mile, and then I can get this diagram which relates the density with the flow. So this gives me a triangular shape if I using this relation. And this diagram is very important to traffic flow. So people give it a term called fundamental diagram of traffic flow. And what you notice that you have a triangular relation, so piecewise linear, constant slope here, and that slope is given by this 10 miles per hour that we have. And then you notice that there's a maximum flow. So there's a capacity. So road have finite capacity. So there's a maximum flow. And then this point separates free flow and congested flow. So if you are here, your speed is very low. And if you're at this point, which is the jam, then your speed is 0. So that's what, this behavior leads us to a relation of between flow and density and speed and density. And then once we have this relation, and then you can have the conservation of the vehicles, conservation of flow, and that is given by a partial differential equation. This is the basic model that we're going to have. Actually, This is in alerting coordinate that you have an observer at the roadside, and then you measure the quantity. But if you move with the vehicles, and that will be given this equation. And I think most people work with this one. So in terms of, and this one actually resembles in when you discretize it, it resembles the Ka-Feng model that we derived. It's not exactly the same, but it has the same form. And so this is the model that we have the partial rho, partial t, and partial flow, partial x, and which is a function of density, and that is given by this form. And we know very well that when you have, in this case, we have two traffic conditions. One is downstream is heavier traffic, upstream is lower traffic, so this is density. And then we have a shock wave connecting these 2 points, and the slope will be the speed of the shock wave. So these are the slopes of the two branches, and this is the shock wave speed. And what happens? This is a vehicle trajectory. So a vehicle travel from the light side. Once you cross the shock wave, you change your speed dramatically to the lower speed. So, and that congestion can propagate upstream. You have the same density, but you switch side, the light traffic is downstream and heavy traffic is upstream. Then, there's more space to open up, so the traffic will accelerate. And you accelerate, in this case, you have this fan of acceleration, and in this region, the traffic will discharge at the maximum flow, because you have room to accelerate. And for a vehicle going from heavy traffic, once you have hit this edge of the fan, and then the speed will immediately change to maximum speed. So that's what we call an acceleration shock. So in both cases, the speed of the waves are, the acceleration and deceleration are infinite. Okay, so that's the in those models. So how realistic are these models? And I think we can look at first the parameter, the response time t, and if you take the interpretation of the vehicle lines from 15 to 20, 25 feet for a vehicle, and a car length plus some safety buffer. And what we get the time is 1.2 to 0.2 to 1.7 seconds. And then we can plug into the equations, and we get the maximum flow. Okay, we get the maximum flow. And also for the 1001 rule that I counted on my iPhone, it took me average 10 runs 2 seconds. So that's greater than the one car rule. So it's on the conservative side. And then if you look at the road design manual, it's even more conservative. It gives you the value of 2.5 seconds you should use for people's response time. So if we look at this different vehicle lengths and we look at the maximum flow you can get, and when you have a vehicle length plus a safety buffer is 20 feet, and then it gives you 2,263 cars per hour per lane. And this is what the highway capacity manual, looking through numerous cases, and what they get is 2,000 to 2,400 vehicles per hour per lane, cars per hour per lane. So this falls well into the range of that. But if we have 1 second, then it's 3,000 vehicles per hour, about, and that's very high. But sometimes if you look at the left lane traffic, you can actually observe that high value, maybe not close to 3,000, but more closer to 2,800. And if you look at arterial streets, then the values are more around 1,800 vehicles per hour. So, and that is consistent with the observations. And also, if you look at the speed of this branch is given by 10 miles per hour in our 1 car per 10 mile 1 car length rule. And if where's my so here's another real data, the piece of data that to check with the assumption of the triangular diagram. And this is a highway near Davis. And then if you look at the plots from, this is occupancy is a measure of density, and then the flow, and you can look at this left lane and the black is middle lane, and then the red is right lane. And this is the plot for this location. And there's a bottleneck here, and then the left lane, middle lane, and a right lane. And one thing you notice that different location tends to have different shapes, differ a little bit. And they have the maximum flow is between 2,500, and also here it's about maybe 1,700. So there's a lot of noise, scatter. Okay, it's not a very nice linear shape because there are changes in vehicle lines and in driving, behavior and reaction times. And you can see there's roughly a triangular shape, but for the rightmost lane, it's not triangular. It's look like a curve. The transition is more gradual. And that's because on the right lane, there's entry and exiting vehicles, and they interact with each other. So the model doesn't account that. So the shapes are different. But looks like a triangular diagram. It's a reasonable, approximation to traffic. The good thing about triangular diagram is greatly simplifies solving the shock wave model. Yeah, because it's piecewise linear, and then you can really just take a piece of pencil and paper. You can work out the solutions. And also another thing is about this parameter, the slope of that branch, which represent the propagation of waves on the highway. And this is a case study by March and Cassidy on a Canadian highway. And you can see this propagation, and they're roughly at constant speed, and they all looks like parallel. And they reported that it's falling in between 13 and 15 miles per hour. And we measured this on the arterial road, and then we get a value between 15 and 17 miles per hour. So 10 miles per hour is little on the low side, but there's a, and this is on the high side. I think this part of the reason is that people leave more space when they stop at the intersections than in these situations. But still, it's in the order of magnitude. This assumption, and of course we can vary those parameters to change that to match those values. Another thing I want to point out is sometimes you observe this type of diagram that you have here, and then suddenly all the points are following here, and that's a good indication you have a bottleneck. Here is somewhere you have a bottleneck, like a lane drop, and that constrains your capacity. So once you get congested here, you'll never flow more than this. So although initially you could, without this bottleneck, your diagram could be like this, but since this bottleneck constrains the flow, then you observe this and that. So that is when you have bottlenecks, you need to take into account. It's not that the diagram becomes this, sort of a discontinuous and multi-valued. And then next thing is that although the triangular diagram is very simple to calculate, but still when you want to do large-scale networks, you want to compute them rather than by hand using computation. So here we discretize the road by the time and with the interval h, and by the cells with the size delta, and then that partial differential equation, we can use a finite difference equation. It's the density at time t plus h will depend on the density of time before, and also the number of flow coming in and out of this cell, and divided by the space and time left. So the key thing is how to calculate the inflow and outflow. And we introduce a concept called a demand and supply, and the demand of a cell depends on the density. So it's using this branch, and once you have the maximum flow, then it reaches maximum. So this is the demand, and this will be the supply. The demand means how much traffic wish to leave the cell. The supply means how much traffic can I accommodate in the cell. Okay, and for if you have traffic is not congested, then the actual flow will be your demand, but your supply is higher because I can accommodate a much higher flow. I have more room. But when you are congested, your demand, there are more vehicles wish to leave, but you cannot accommodate that much, so the supply is low. And the key is that for a cell, the actual flow is the minimum between the supply of the downstream cell and the demand of the upstream cell. So there's interaction between the cells. It's not just depend on one side, it depends on both sides. And then in the road, we don't have just one single stretch. We have networks, and there'll be road merged together and the road, splits. So we can extend the model to model them two in road merged together. And the key is one is this is the merging priority. When you two roads and the competing for the space, what's the proportion that people can, the different branches can come in. And then you have the total flow going through the downstream three. The key is that the total flow will be the minimum of the combined demand of this and also the supply of the downstream. So it's the minimum of the two. And then as for the splitting, you can have different rules. One of the rules that we come up is proportional to the demand. So you have higher demand, then you have more traffic coming in. But also you can use number of lanes to express the priorities. Or you can have freeways have higher priority than the entry ramps. So you can come up with different merging priorities. And then for splitting a diverge, again, we have this split proportion. And in this case, it doesn't depend on priority, it just depends on which direction you want to go. So depend on your OD, the composition of which branch you want to go. And the total flow in this time is determined by this, and that formula is given by Carlos de Genzo. It's minimum of the demand, so how much traffic wish to travel, and also the augmented supply of the downstream, how much room can we accommodate how much traffic. But this thing has a serious consequence, is the blocking effect. Look, if this branch is completely blocked, the supply is zero, it's jammed, then because of the FIFO you have, then it will block this traffic, so there will be no flow coming into that. So there's a serious assumption. In real cases, there may be still some people coming there, but in most cases, I think this is kind of realistic in the sense people were blocking each other, and then you cannot leave, and that as a consequence to explain the gridlock on city networks that you're going to observe. So, and that's the basic theory that we have. And then from that theory, I want to show you how we can apply that to real life situation. One thing, I want to explain three phenomena that we often observe. One thing is we call a phantom jam. It's oftentimes you're stuck in traffic, inch along, and for half an hour or maybe longer, and then once you get out of that, you're flowing fine and you never find what's the cause. So you wonder, what happened, and some people maybe say, oh, that's a phantom jam, there's for no reason. But really, most of the time, there was a cause. It's just because the nature of flow propagating, then you don't observe it. So let me explain why is that case. It's here. Suppose there's an accident happening at this location. So this is time and this is a space. And this accident blocks some lanes. So you have some lanes blocking, and therefore you only discharge this much flow. And what happens is you have this much flow coming from here, and you only can discharge this, so you have a shock wave. So you generate a shock wave, congestion wave, and also people, once come to the shock wave, people slow down. You travel at 20 miles per hour instead of 60 upstream. For some time later, like this time, the accident was removed, and then this road is open. When it's open, and then there's more space and people can accelerate, right? So from the theory, then people will come to this point. So you'll travel at 60 miles per hour, and then you have an acceleration shock after that. So this is the acceleration shock that we think. So after people coming from here, then they accelerate back to 60 miles per hour. So look at what people experience. All the people travel before this person, he or she will see the accident here because it's still there. But how about the people who travel after here? And let's say this person, and then she travels here, slows down by this congestion caused by the accident. And then when the acceleration wave reach here and she speed up to 60 miles per hour, and then when she comes to here, the accident is already gone. So there's, she doesn't know what caused this. So because of this propagation nature, and then all the people travel after this, and before this person will experience some congestion, but you'll never see the reason why this. And this is very different than fixed bottlenecks. Like, for example, you have a lane drop, and then you will know, because past the lane drop, then traffic will be free flowing, and you know what caused that is just too much traffic for too little capacity. But in situation like this, some of you won't know what caused it, and this may not be an accident. It can be a moving bottleneck, like a slow truck comes in climbing a hill, and then slows down a bunch of cars, and you get stuck. And then once this, over the hill, the truck speed up, and again you generate a similar phenomenon. So that's one of the things that this theory can explain. And the second thing is that when we know that these lane drops, the merge lane drops or just a lane drop, and that can be a source of a bottleneck, create congestion. And also, once we're stuck in congestion, we never move at a constant low speed. When we speed up and slow down, we call this stop and go waves. So I want to show you here is that your behavior at the merging here, your choice of location, can actually produce this stop and go traffic patterns. I was wondering how many of you are sort of early mergers. Once you see the sign, and you'll merge, and raise your hand. Oh, not that many people. How many of you are merging the last minute? So most of the people are in the middle, huh? So merging in the middle, but that's not what we found in the data. So we look at some construction sites, and we found that so you can see this the number of merges at this construction. A lot of people actually merge fairly late, at that point, and then there's quite a bit of people merge early, and then people merging in the middle, and the highest 2 points are early and late. And also, this is when you have high speed of travel. And look how many people merging late when the speed is very low. There is still a good percentage of merging early, but there's much higher percentage merging very late. And so, although the merging location can happen at any time, but suppose you have predominantly two merging locations. One is early and one is late. And what would happen? What's the consequence of that? So we'll look at this situation, and we model that as emerging network. So here, this will be the early mergers, and they'll shift to the through lanes, and then some people will keep on going, and this will be the late mergers. And then we can model this process as a network of interaction. And then, so this is a dominant early merge location, and this is a dominant late merge location, and this is the shorter lane, and this is the through lane. And then we apply the network model, that kinematic wave model, to this, and then we can solve this problem and simulate that. And we found that under certain conditions, that means one is you have to have sufficient traffic to get the road congested. And second is there has to be the right proportion of traffic doing late merge. So if you have very few or very high, then you won't generate oscillation. So if you have those right conditions, and then we can generate these stop and go waves. And this is the flow. You can see the fluctuating flow on the shorter lane and the fluctuating flow on the through lane. The thing to take home is that this period of these oscillations is highly related to the lengths between the two merging locations, and also the speed of the traveling speed, and also the speed of the waves. And good thing about this explanation is that this period is roughly in the order of several minutes. And depending on the merging location, it can be longer and shorter, which is very different than you using the car following models and instability. And remember, the T, capital T, is in the order of seconds. So in some of the instability, you can still also get oscillation, but their magnitude is quite different. So So here, we can see these stop and go waves by looking at the proportion of the merges. And I want to explain what happens that caused this. Here, if you have people merging late, and so these two merging flows is higher than the capacity, so you generate a shock wave that will go upstream. Once you reach the point of the early merge, and then this shock wave will reduce the inflow to the shorter lane. And that reduction of inflow, once you reach here, and since the flow is lower here, and then you generate an acceleration wave, so going backwards. So that acceleration wave will reach here, and that again will increase the flow because this is a better condition, light traffic, and this will come back here, and that will go back to the shock wave again. So this ping-pong effect by more traffic coming in, and then you get a shock wave and reach upstream, and that will reduce the flow, and then you get an acceleration wave, and that will increase the flow, and it's going back and forth and create that stop and go oscillation upstream. So that is the mechanism that caused those things. Another thing that I want to explain is gridlock. This is a famous picture that if you search Google and you often you see a traffic jam, and you come up here, and you look at this. It's fascinating because you can see this lock is self-locked, and then there's empty space, but the vehicles cannot move, and there's an empty space, and so but people get stuck. The reason that people get stuck, it's we can model this traffic circle as a railroad with entry and with merge and diverge points. And we can apply this merge and diverge models to the train. And when you have priority for the merging traffic, that means either people force their way in, or there's more flows coming in from here. And what happens is then you generate congestion here. And once you generate congestion, remember the low flows here. Will affect the flows here, the people coming out, because the flow coming out would depends on the supply here and the supply here. So you get the supply lower, and then that will generate congestion here, and that mechanism sort of going around, and then you have more traffic coming in, and you get the railroad will get a little more congested, and that will affect the other one, and then gradually you have traffic moving, basically stand still. You get stuck. So there's a self sort of locking and destructive mechanism to gridlock the traffic, and this is not really unique to railroads or traffic circles. Even in regular networks, let's see. I have a grid network here with so this is a synthetic network. We use a simulation equivalent model, and we have 19 by 19 grid, and with 256 OD pairs, and then we simulate for 1 hour, and then we look at the demand sort of in this 1 hour peaks and then subsides, and we implement a couple models, and I won't go into detail of this model, but this model is the one that I explained before. So it's called a CTM, it's a standard automata, a transmission model. And then we get gridlock situations in this grid network, and I'll show you the patterns. So basically, when the conditions are right, then you form a rain, and then the traffic here just gets stuck. So people moving this way cannot move, and they cannot move here. So the queues will perpetuate. You get gridlocks in regular patterns as long as you have this interlocking with the path dependence and also OD distribution. So people, in other flows, if you get stuck, then you just change your direction. You just change your destination. But in most of the cases here, since people have origin destination, they're not willing to change their route, and then although there's space, people are not willing to use this, and then you get stuck. So these are using the model that we explain some of the phenomena that we observe in everyday life. And the next set of slides, I want to show you some of the applications that using this model. One thing is doing access control. For example, in that traffic circle case, we can install traffic lights at these merging locations, and we can control the amount of traffic coming in, so you can prevent any congestion inside the ring. And that should be very simple to do. And once you know the capacity, and then you can really measure the capacity, the flow here, and just control below the capacity. Or you can apply tolls to affect the flow here. But in a more general network, then you can formulate that problem as really a nonlinear program. You can maximize or minimize the total delay in the system, and subject to flow conservation and also capacity constraints. What I want to point out, so you can see all these mathematics. I'm not planning to explain the details, but I want to point out two things. One is this problem is non-convex. It's because this constraint, this product constraints. And since it's non-convex, also you don't have unique solutions for that. What this constraint is about is it captures the blocking effect. Remember, when we have the supply and demand, if the supply downstream is zero, then the flow will be zero coming. So you have blocking, and that captures those effects. And once you have that, then you have a very complex problem. So far we haven't been we work on the problem. We haven't solved a general problem, but we found out that in the case of many to one networks, what it means is that many origins to one destination, like everybody going to a CBD. In those networks, you can control the traffic at the perimeter and eliminate the queues inside the network, and then have all the queues in the perimeter. And that provides you the best solution, the minimum delay. But in practice, that may not be feasible because you don't have storage for the long queues, or people may not be happy to sitting there for a long time. And that's what happened in Minneapolis, because Minneapolis, their signal metering is they want to maintain almost free flow on the freeway, but the queues are backed up in the ramps, and sometimes you can back up for delay for 15 minutes. And the average travel time in Minneapolis is 17 minutes. So people, talk to their Congress, and they were mandated to do experiments and see, whether this metering is actually improve the situation or not. But if you can, have managed to schedules and delay the traffic at the periphery, and then you can you can keep all the queues outside and inside, and that's in a way it's good to manage, because when you have free flowing inside, then it's very easy. The travel time is very reliable, and it's easier to schedule, and also you probably reduce the number of accidents. In the general networks, it's a very hard problem, because it's for those of you who do work in operation research, it's a dynamic multi-commodity flow, and with capacity constraints, and also with the blocking effects. It's a highly nonlinear problem, and so we haven't really solved this analytically, but we solved that numerically, rely on heuristics. And contrary to this finding, we found that actually allowing some queues inside can actually further improve, reduce the travel time. So it depends on type of network. The solutions can be different. My final application is a real case study that we did for the city of Sacramento. In 2008, the city of Sacramento wanted to close one direction of the highway near the Freeway 5 near downtown Sacramento for a couple of months for reconstruction of this section. And they want us to study what would be the impact of this closure, and also compare with two other alternatives. One is a 90-day partial closure. You close only 2 lanes and some ramps. And then the other is a 110-day, they call A plus B plan. Also, you close partial of the lanes and different ramps. and we want to look at the statistics on travel time and distance and vehicles miles traveled and also emissions and fuel use, and look at these different alternatives, how they compare with each other. So before we did that, is that we have a tool that we implement the traffic models that I described. Not just the kinematic view model. Also, we implement a bunch of other models just for comparison purposes, and also we implement the node model and some of the operational characteristics like signal control and meter ramps. And then in this simulator, so we can, given the demand to the network and also the people's routing behavior, and then we can estimate what the traffic conditions will be and calculate these statistics. So here's how the network looks like. That we coded in the Greater Sacramento area, and this is the stretch. Here is the stretch and the reconstruction, and also we collected data from the network, that including the topology of the network and what the construction plans are and different traffic management plans, basically the signal operation, and also the information that the agents are given to people to advise people taking alternate routes and avoid certain areas. And we collected traffic counts, and we ran some cars to collect travel times before the study. And also we collect the capacities and speed of the road. So a lot of things that we have to get to model the city. And this shows you some of the data we collected on the traffic flows during the actual closure of the northbound direction. And also we collected the baseline data. And then we calibrate the model. In the collaboration, one thing we have to estimate the OD flows, the origin destination flows from the traffic counts. And the other thing is how many routes people sort of select or keep in mind when they do the route choice, and how many people have real-time information or they are willing to change their routes when you have encountered congestion. And we calibrate this, and we found that have 3 or 5 pre-selected routes in their choice set, and then 50% of the drivers are willing to divert when they have traffic conditions, and then often they update their travel time every the route every 5 to 10 minutes, and this is the edge, the simulation time interval. And after the calibration, and we run the simulation, and we don't get into the gridlock situation, and then we compare with the observations we have and see so how that close with the real data. And once we calibrate that, and then we can run different scenarios of the construction plans with the given set of OD demand and so forth, and then we can actually look at the congestion patterns on different routes, and by checking them with the observations, see if the congestion pattern makes sense. And once we've done that, then we look at the statistics. So we compare the baseline, which is before any closure, and then the actual full closure of one direction, and versus the hypothetical, the alternative A plus B plan and 95-day plan. And we look at the total trips in the network, because perception of congestion, you have people taking vacation ahead of time, try to avoid that period. So there's a reduction of demand and during these different scenarios. And some are by estimate and some are observed. And we can look at the total delay in the network and the average travel distance, and travel time and total vehicle miles traveled and so forth. And we also have estimation models based on the speed on the link, and to calculate the fuel consumption and different emissions for like carbon dioxide and so forth. And then you can compare this statistic and recommend what type of plans is give you the best performance in terms of the travel times and in terms of the emissions, environmental factors. So those are the applications that we did. And then I want to, by concluding my talk of looking at the other aspect of traffic that this model does not really explain and capture. One thing is instability. We know in traffic sometimes small changes at the right conditions can grow and then create traffic problems. Here, this model is always stable. So you want to create traffic jams, then you have either in the network effects or there's big disturbances. So we cannot use this model to model the phenomena of instability. And the other thing is that if we look at some of the transitions of traffic flow, and this is the flow and this is the density, it's not a very nice triangle. Actually, the deceleration and acceleration often follow different paths in the diagram. So people call that hysteresis. So this model definitely does not capture this because there's only one diagram. It's actually, we observe there's multiple passes you can have. So that's one thing that a limitation of the model. And the third feature that we don't capture in the model is if you look at some other plots, and oftentimes we see an abrupt drop in the flow. So people, and that can be up to 25%. So because the merging, and sometimes because the merging, sometimes because instability, and you can have this drop, and then we call it capacity drop. So in the model, we don't have the capacity drop, we only have this portion. So the model does not explain this capacity drop if that's a serious problem. The other thing is, so far all the models are stochastic, deterministic. But we know in real life, drivers are different drivers have different reaction time, the vehicle have different size and performance. Also the road have there's curves and there's a narrow. So there are a lot of randomness in the, and if you look at the plot of the velocities, and you can see a lot of fluctuations particularly in the low speed regime. And then if you look at the transition on the diagram, so these are connecting by the time. Before, we don't have time in it. Now if you're collecting the time transition, you can see there's a lot of, it's hidden noise. So we need to consider this in the future models. There are efforts to capture, for example, the nonlinear effects and the instability, and then in the car following models, and also in the macroscopic models. I think Professor Lydia probably will recognize some of this, and this is very similar to gas flows in pipes, the equations. You have the conservation of cars, and then this is similar to the momentum equation in those models. So these models can give you instability, and also they can explain some of the hysteresis. But in any case, and those models all have the speed and spacing relation as a central component. So you need to have that behavior. Otherwise, you could just describe river flow or gas flow, not traffic flow. So this is the key to these models, just like in the shock fluid model. So finally, I think it's an exciting time to do transportation because all this talk about the autonomous vehicles and Google cars, and in the future the cars will drive themselves, and so that creates a lot of excitement and also opportunity. Here I just want to share with you, what's in terms of from the traffic flow, what's these autonomous vehicles do to traffic. One thing I talked about is there's a lot of heterogeneity in traffic, in drivers and things. But if we have Google cars and the GM cars, or autonomous vehicles, we're reducing the billions of drivers into just a few types. So it creates uniformity. I think the life of a traffic flow model will be much simpler because you can. So all this random heterogeneity will be gone. Instead of trying to figure out, what is his driving behavior and rules and hidden. Now we can actually design the control logic of the car to follow exactly a triangular diagram. So now we are going back to what we assume people would do, but people, fail to do. So, just to give you an example, if the autonomous vehicles can talk to each other and platooning together, and then we can control, we can set up a very simple PID control, and basically, here is what we recommend people to do. And for using the two rules, and that will give us triangular diagram. But as humans, we're not perfect machines, so we cannot do that precisely. But now we can ask the autonomous cars to do that much closer than to here, because look, this is the relation from here. So we have this relation, and then if you deviate, then we try to suppress the deviation. And also, we know the leading car vehicle, and also we try to have the second term is to reduce the variation between the speed. And the third component is the acceleration of the leading car. So by vehicle-to-vehicle communication, we can have that information. And then what we can do is that for the human driver, one is this T is stochastic. Even they follow the rule, it's stochastic, and also it's in the range of 1.36 to 2 seconds. And the tau is the time delay here. And in the autonomous vehicles, because of this control and communication, we can considerably shorten the time gap between the cars. And for, if you're on a special lane, you can reduce the gap to 0.6 seconds, and still you can maintain the platoon stable. And that will give you increase the throughput dramatically. It depends on the size of the platoon. You can from a low 1,500 all the way to almost close to 4,000 vehicles. And that's almost like double a lane, right? The capacity of a lane, because we're talking about 2,000 and 2,200 vehicles per hour. But there are, so I think definitely in terms of throughput, and autonomous vehicles can, instead of building more lanes, we can use it to improve the throughput. But there are a lot of other factors coming into play, the human factors. So it's still, there's a lot of problems that we need to look at before this is being fully realized. And one thing I think is, for safety reasons, all these car manufacturers probably, instead of setting very low time gap, they may actually setting very high time gap, because they don't want to get into a bad accident and then they get the bad publicity, and that is not good for their autonomous vehicles. So initially we may not see high throughput, we may actually see low throughput. But autonomous vehicles can offer other opportunities, because if we know the vehicles and we can have full control, then we can schedule the system. And then we can schedule the arrival, we can schedule parking. So there's a lot of opportunities to use autonomous vehicles to reorganize our traffic. So finally, by concluding, I think vehicular traffic, unlike some natural flow, and it's both simple and complex. It's simple in a way that from a very simple rule, we can derive a traffic model. And that actually can explain a lot of the phenomena that we observe every day. It's complex because from these simple interactions, then there's very complex phenomena that can come up, like the gridlock, the stop and go waves. So all these interactions will produce a complex phenomenon once you put them together. And also we know that some of the features we still are struggling to model, and also all this stochasticity and things like that we have to account for. And until the days of the autonomous vehicles, we need to address the stochastic elements in the system. So to look in the future, I think the autonomous vehicles in a way can simplify our life, particularly model traffic, because now we can really design what traffic flow looks like. And also it increases the options for control. As I mentioned, you can schedule the system, we can have reservation systems, and also you can have the autonomous vehicles as a flexible transit and serve the the last mile problem, and also can reduce car ownership. If the autonomous vehicle can come to a door 2 minutes before you leave, and then why do you need a car? So maybe we can just dial an autonomous vehicle and come here. And then if we don't need a car, maybe we can get rid of the garage. So your house will occupy less land, and that maybe also help us building more compact communities that can promote public transit. So there are a lot of opportunities here, but also there are a lot of obstacles that we have to overcome. And then I want to thank the funding agencies for my research and also the collaborators that contribute to some of the work. Thank you.
Questions?
I'm no expert of traffic flow. I study hydrodynamic waves, right? But I have two thoughts. One is when you mention autonomous vehicles, I think it will be very interesting to consider. It will be a long time before it will be autonomous vehicles homogeneously, right? So I think it will be very interesting to study heterogeneous swarm behavior where some of the vehicles are not autonomous, right? And I think that's really interesting to me because then I've looked at heterogeneous swarming of different kinds. And so your assumptions, like platooning and so forth, are quite idealized because you assume every car is autonomous. In fact, if you introduce one human car into the highway, it might completely disrupt the behavior, the predicted behavior. Right?
Yeah.
And the second thought I have was, what do you think about the sort of coming of popularity of these crowdsource-based routing apps, right? I've completely changed the way I commute because of these apps, okay, completely. I mean, when you talk about 5 alternatives, right? I have now 50 alternatives from the 12 miles from where I live to MIT, right? And have people been looking at that? Because this is it might have instabilities now because if everybody follows it, right, they are using the information that they see and feeding back, and then everybody goes after. So you will have oscillations that are not present now in the system, right?
Very true. I think people call that herding effects because if imagine there's only a few apps like Google or Waze, and if every people see the same information, and then if people are moving to try to avoid the route and moving to the similar routes, then you can have oscillation between the congestion routes. So I think that there has to be some randomness or something to build into these apps. So perhaps not every so you kind of distribute the swapping between the routes. Actually there are people try to game this. And one person, told me that when he sees the Google map, the red, the routes with a lot of red, and he actually purposely go to there because he thought, other people will try to get away from that. And then, if he traveled there, and then by the time he arrived those locations, then maybe the traffic would be gone.
In the context of a network, the app becomes like a supernode, like a small world situation, right? Because the app actually has information that is like global, right? Not limited by a local area, right? Which is something that had heretofore never appeared in a problem like this, right? There had never been there has never been a small world effect, like where what you see is dependent on the local, whatever. One square mile, 1 block situation, right? Because now you have information from far away being integrated into the local behavioral solution.
Right. The one thing about this is that these Google apps, all these apps will give you the current situation, the current time, and then when you travel, as you move along, this situation can change, right? So there are people who keep on adjusting, based on the situation, and there are some people, just based on their historical experience. And they may just stick to certain routes. So really, there's a very interesting subject that with data we can look at how people behave in that way and how that can factor into the network flow. I think probably Marta would be a good person. She just left to look at that, and she used the the phone data to look at people's mobility patterns. And also about the mixed traffic, I think, Carolina, you were studying the autonomous vehicle mixed with regular vehicles and how that. So there are studies looking into these problems, and those are sort of exciting new things that the transportation profession is looking into.
If I could just add to that, I think that highlights that example that although we might have less of a need to actually model driver behavior, we still have a significant need to model behavior of other decisions and how we react to all the information that these automated or connected vehicles are giving us. So I think the behavioral complexity that you were mentioning before is still very prevalent, but it now is looking into or more focused on other decision or choice dimensions than just, you know,
I was
following the
thinking about possible future apps, ways to, 2.0, which is predictive, right? Because you can put these models in, and they could actually, you don't have to game it by heuristics. You can actually, they will actually improve the capacity by, they're doing real social service rather than just helping people who have the app to do better than the people who don't, right?
And also, this system there's a feedback loop because you're crowdsourcing from the people, and people look at the condition generated by this source, and then that feedback can change the behavior of the people, and that also affects the your data. So yeah, it's a whole different ballgame in terms of modeling. I think.
Maybe even game theory, right?
Yeah.
Predictive model with game theory.
Yeah.
So that's been studied for a while in transportation in terms of how do you give forecasts that are consistent with how individuals are going to react to that information. I don't think any of these apps are using that. Maybe that's more of our work to actually convey that research to them so they actually use it. But yeah, that's.
Yeah, so far, I think the apps, we're seeing is more simple display of the information, and then you make your choice. You choose, but that is also feedback to because your choice will affect this traffic condition that show on the apps. But I don't think Google or any people, have look into this problem. Yeah.
Other questions? Okay, thank you very much.
Thank you.
So, I was thinking about a lot of the complexity of behavior.